saying when t is large, so this is t, and this is not 0, by the way. This is, I did a mistake over here. So this is not 0, but 0 is very far from the place. But when t is very large, when t is bigger than a certain number t, then we can assume that it is very close to this process, okay, to this straight line that we draw over here. So it might be that at the very beginning, things become not necessarily very true. It can be anything, but when it comes to this, then this becomes very small to one another. So here I said what is B, this is B, and this is A. So I just mentioned them over here. So the variance of xt is, these are constants, right? So this is a constant, this is a constant. So the variance of a constant is 0, and we are assuming that x0 is constant, so this is 0 as well. So we're left with this, the variance, which is the same as the previous thing. So we're left with, which is equal to the same variance of the autoregressive of order 1 process. So an autoregressive of order 1 with a strand is the same as an autoregressive, the variance of it with an autoregressive. So they have the same variances. Obviously, you can refer to the lecture notes in the Google Classroom. So if I want to take you to the Google Classroom, so if you go to Google Classroom, you will see that you will see here in the lecture notes 8, everything is explained over here as well. Okay, so they tell you why this is the same covariance stationary. So here it is what we're talking about. Okay. Let's go back here. So here I gave you the same example as it is in the previous lecture notes. So this is an example of how things would look like. This is a trend, an autoregressive of order 1 with a trend. You see the trend over here. And you can see that at the very end, you will see that things become somehow like a straight line, almost a straight line here. Okay. Yeah, that is mainly it. Now we're going to talk about the memory of a process. A very different from concept is what is known the dependence structure of how things are related to one another of a process. The dependence studies how strong or how weakly a random variable xt depends on xt plus h, where the differences between them is only the lag, which is h. The differences between t and t plus h, like t minus absolute value of t minus h or plus h, and absolute value is equal to minus absolute value of minus h, which is equal to h, and therefore the time distance between them is given by h as h gets large. Okay, the memory of the time series measures the extent to which the future past can be predicted knowing its past history. So what I'm trying to say here is the following. So let's take an example. An example could be shown that in some occasions we might have that the covariance of xt plus k is given by a function of k. Now what memory studies is how fast that this function decays. So if this, let's say, it's exponential k, then this means that it goes to 0 really, really fast as k goes to infinity. If it was that this is equal to radical k, then this goes to 0 more slowly than e to the k. So f is a function of decay, where it is assumed that as the time elapsed k, which is the difference between this and that, goes to 0, goes to a bigger number, the value of fk decreases. So things are dependent very weakly, or dependent. The dependence structure between events is almost negligible as the time elapsed between them goes to 0, and this is somehow very similar to what's happening in reality. And remember, we use mathematics to mimic what's going on in reality. Now when it goes to 0 as being claimed, if this function over here goes to 0, what does this mean? Sorry for that, there's something wrong with my computer. So if this goes to 0 as k goes to infinity, what does this mean? This means that things become asymptotically uncorrelated. So it is asymptotically uncorrelated. Why? Because the covariance structure between two things, when these two things goes to infinity, the time elapsed between them goes to infinity, things become not related. Okay, so let's give a certain graphical explanation of what do you mean by asymptotically uncorrelated. First of all, as we have just mentioned, is that the memory of the time series measures the extent to which the future past can be predicted from known history. So we spoke about this, and we want to talk about how would this graphically mean. In practice, the length of the memory is measured roughly by the infrequencies of the series crossing the mean. So you can see that, for example, here it is very frequent that the process, goes back to the mean. We call this as a mean reverting process, and this means that the memory is somehow very low as compared to memory that is very large, which means that there is some relationship. Here it is closer to be independent, as you can see. So the memory is very short, and maybe the memory is almost zero. So the covariance, for example, between a process between, let's say, if let's say we are talking about an example here, I'm just going to give you a certain example. So let's say here we have xt to be a normal random variable of mean 0 and variance 1. And we know that since they are independent, so the covariance of xt and xt minus k is actually equal to 0 for every k belong to R, right? So for every k belong to R, the covariance between things are 0. So this means that almost they are independent, right? So when things are independent, it is less, and the mean of xt is equal to 0, then we know that the observations are gonna cross this line here, which is y equal to 0, so many times, because we know that this cannot predict the future, right? Somehow maybe the future could be predicted only like by knowing that it is gonna go back to the mean. That's basically it. Now let's talk about forecasting. Forecasting is an important part of econometric analysis. To some, it is maybe the most important thing that people study econometrics for. It is somehow to tell you what is gonna come based on the previous past. How do we forecast economic variables such as GDP, inflation, exchange rate, stock market, or stock prices, and unemployment rates? All of these are very important questions. And obviously, the better model you have, the better your prediction would be, right? So that's why we study econometrics, and to assess a policy. Let us look at the particular model before any generalization. So let's look at the YT, where we assume that YT follow an autoregressive of order 1. So this is an autoregressive of order 1. As you can see here, this is a constant term, and this is rho. Rho is the same as lambda that we used to have earlier. So a stability condition would be that the absolute value of rho is less than 1. So for a stability condition, the stability condition would be rho in absolute value is smaller than 1. And since we do not know alpha and rho, we need to estimate them. So if it turns out to be that rho is not equal to 1, then, not less than or equal to 1, then there is a problem, right? Less than. I didn't say equal to 1. When rho is equal to 1, this is a very specific thing that we're going to be talking about, and this is known as a random walk. But let's focus now on the fact that rho should be, in absolute value, should be smaller than 1. So how are we going to estimate this? So as I mentioned, what is a stability condition? So we need to estimate things. And after doing this, the next unknown value of the series that need to be forecasted is based on the value of a time t, which is given by the following. So as you can see this, remember we used to run the regression yt equal to alpha plus rho yt minus 1 plus epsilon t. And what we used to do is we run the regression yt equal to hat is equal to alpha hat plus rho hat yt minus 1 plus epsilon t, no epsilon t over here. When we talk about hat, there is no epsilon t. And basically, since we know this, the problem is sometimes yt, when we say conditional on time t, so basically this is, if we are looking at t plus 1, given that we are at time t. So this t over here stands that it is conditional. So we are living at time t, so we are living at this period of time, and we're trying to predict what will happen in the future t plus 1. Okay, we are trying to see, observe, so this is my eye. We are trying to see what's happened at time t plus 1. So when we are looking at this, we have to understand that there is a certain relationship. At time t, I know what is yt, right? Because I have just observed it. I know what it is. And therefore, we're going to use it as it is rather than using yt hat. Okay? In the next period, I do not know what is yt hat plus, I do not know what is yt plus 1. If I do, then it would be, this guy over here would be yt plus 1. But I don't know it. And therefore, I'm going to be keeping it as it is, which is I'm going to be using the estimate based on this regression model. So you will see that if I continue doing this at time t, this will be, I don't know what this value is, which is some value which is greater than t, so I'm assuming that t plus m minus 1 is some value that is greater than t, and therefore I do not know it, and therefore I have to estimate it. And you see this hat, which stands for the estimate of yt plus, which is an estimate of yt plus m minus 1. And this is very important idea to understand about forecasting, because about forecasting we should understand that we don't really know the future value. And since we don't know the future value, we have to estimate it. And this estimate should be built on the estimated the previous value. So everything is somehow recursively related due to the main assumption we are covering here, which is we are assuming that the yt follow this model. So yt plus m hat is equal to alpha hat plus rho hat, and then we replace the previous point of it. I think I did a typo here. This should be minus 1. Okay, and the same holds when we are talking about yt minus 2. Now it's right, and this is squared, so this is 1 only. This is my mistake here. And if you do this, if you build things accordingly, oh, this is minus 2, it's right, because this is alpha hat plus rho hat yt plus m minus 1 given t hat. So this is the same as that, and that's why we have this minus 2. So I was right here. Okay, and if you do this, if you continue doing this, you will find that this is nothing but a sum of a geometric series, which is a rho hat j from j equal to 0 up till m minus 1 of yt. But this is why it should be yt hat. But we know that yt hat is the same as, you know, what should be the estimated value given time t? It's going to be the same as yt. So we already know this. If you have any questions, please come to my office hours. If not, you can you can always refer to your book. Your book speaks really well about forecasting. And that's basically it for now. The random walk. The random walk is a very important aspect, and it is one of the things that we're going to be using a lot in financial time series. So financial time series such as stock prices exhibit what is known as a random walk phenomena. It follows a random walk, and usually why we call it random walk, it is like